Hello Math 3 students, this is Unit 3 Lesson 5A. I have split Lesson 5 into two different lessons because I think that Lesson 5 assumes that you know more about imaginary and complex numbers than you probably do. I know that you were introduced to imaginary numbers and the lowercase I in Math 2. I believe you also saw some complex numbers, but we need to go a little bit further than that before we actually start on our notes, Lesson 5. So for this lesson, you will need blank paper. There's blank paper on the front table with holes already punched in it. You should have turned in your pages 10 through 13 anyway, and I think Lesson 5 is maybe on the back of page 13, so you don't even have that with you. So grab a sheet or two of blank paper from the front table before you start. So you can see the objectives here. Simplify square roots with negatives, complex numbers, and complex numbers and their conjugates. And we're going to multiply those. And you might not know what that word is, but you'll learn that during this lesson. As we go through this lesson, you're going to want to just write what I write. So you can always pause your video and copy everything you see on the page, or you can just follow along with me and write as we go. Sometimes we end up with square roots for answers. So we have radicals in our answer, and we need to simplify that answer. If we want the most accurate answer, we want to leave a radical sometimes and not round a decimal number. So that's what we're going to look at here first of all, and then we'll move on to our imaginary numbers. Perfect squares, I want to look at those first. So numbers that we call perfect squares are numbers that we get when we multiply a number times itself. For example, 1 times 1 is 1. 2 times 2 is 4, and so on. And so as we write these numbers, we notice that each of these numbers is a number that when we multiply a number times itself, we get this number. That's called a perfect square. 1 is a perfect square. 4 is a perfect square. 5 is not a perfect square because we can't multiply a number times itself and get 5. So let's go on and list on down. That's 5 times 5, 6 times 6, 7 times 7, and so on. We're just going to list the first 10. So these are the first 10 perfect squares. These come in handy. Just memorizing these comes in handy when you're simplifying square roots, and I'm going to show you why. Okay, so let's look at these 4 square roots over here and see if we can simplify these in some way. What we want to do is we want to look at the number under the radical and say, okay, is there a factor of this number that is a perfect square? So with 20, of course, 4 is a factor of 20, and I don't see another number over here besides 1, and 1 really doesn't count anyway because 1's not going to help you out at all. So anything besides 1 over here that's a factor of what's under the radical is going to help us. So what we can do is rewrite square root of 20 as square root of 4 times square root of 5. And then we can take the square root of 4 and bring it out from under the radical and leave the radical with the 5. Now, of course, we know that square root of 4 is plus or minus 2. For our purposes during this lesson and during this part of the unit, we don't need to worry about plus or minus anything. We're just going to do the positive version of the square root. So square root of 20 could be simplified as 2 root 5. Square root of 18. Well, 9 is a factor of 18, so we could rewrite this as square root of 9 times square root of 2, which would be 3 root 2, because we take the square root of 9, and that is 3. So we can pull that out from under the radical. Square root of 50, 25 is a factor. So if we want to still, continue to break this down, 25 times 2 is 50. Pull out the 5 from here, square root of 25. So that would be 5 root 2. So if you were asked to simplify square root of 50, you would simplify that to 5 root 2. All right, last one here is square root of 1,000. Of course, 100 is a factor. 100 times 10. So we break it down that way. And then we take the square root of 100, which is 10. And so square root of 1,000 simplified is 10. So we run into a little difficulty when we have a negative under the radical, because we know that there is no number that I can multiply times itself that's going to give me a negative number. When you have a number under a radical, that's what you ask yourself. What number times itself equals this? There's no number times itself that equals -4 or -1 or -2. No real number anyway. But what we do say is if you see the square root of -1 or -4 or anything like that, what we use is an imaginary number. And we just call that imaginary number I. We use a lowercase cursive I to denote the square root of -1. And I believe you guys did a little bit of that in math too, you should have, where you just saw, if you saw a negative under the radical, you pulled out the I. And I is the square root of -1. So anytime you see a negative under the radical, you can take that I out. So let's talk about what square root of -4, how that would be simplified. Well, we could write this as square root of -1 times square root of 4. If you just want to think of it that way, you don't have to write it that way every time, but you can think of it that way. Square root of -1 is I, and square root of 4 is 2. Now you want to write it this way, 2I. Just like that was a variable, it's not a variable. It is the number I, which is square root of 1, but we want to write it like it was a variable, but write it in cursive. Okay, let's look at this one. Square root of -2. Now, this is square root of -1 times root 2. Root 2 is simplified. There's nothing else I can do with that but write it as root 2. I can simplify this part, though. Square root of -1 is I, so I would write I root 2. That's how that would be simplified. Square root of -100, 10I. Okay, square root of -1, square root of 100. Square root of -50, we did square root of 50 on the previous slide. It was 5 root 2. This time we just need to add in the I, 5I root 2. Square root of -18, I think we did that one too, didn't we? Yep, 3 root 2. Square root of -18, 3I root 2. Now, square root of -a squared. Well, what is the square root of a squared? So I can break this down. What times itself equals a squared? A. So the answer to this one would be AI. Square root of -1 is the I part. Square root of a squared is A. Okay, so this one's going to have 3 parts. I'm going to rewrite this one as square root -1 times square root 4 times square root n. The only thing I can't pull out from under the radical is this one right here, the square root of n. So this one's going to be square root of 4 is 2. Square root of -1 is I. Square root of n is just root n. Okay, so anytime you see a negative under radical, you're going to pull out the I, the imaginary number. Okay, so let's talk about complex numbers. Complex number is a combination. Let me just give you a definition. A complex number is a combination of a real number and an imaginary number. Let me show you what it looks like. Typically, you see it written as the real number and then the imaginary number. So you might see something like 5 plus 2i. That is a complex number. They are not like terms. I can't combine them in any way. So I have my real number, I have my imaginary number. You really don't want to write this like this. This is not standard form. This is standard form for a complex number. So you want the real number first and then the imaginary number. That doesn't mean you won't see them written like this, but this is how you want to rewrite it. Another example would be 1 minus I. That's a complex number. And then one more would be 10 plus 3i. They can be combined. So like if you have, let's say we'll combine this one and this one. 5 plus 2i plus 10 plus 3i. The 5 and the 10 are like terms. The 2i and the 3i are like terms. Just like if that i was just a variable. So 2i plus 3i is 5i. So if you had that where you needed to combine them, you can combine like terms. Really, when you see complex numbers, you're always going to see the two terms. You won't see, you know what, I'm going to wait, and I'm going to talk about that in a minute. I was going to say you won't see I squared, but I'm going to tell you why in a minute. Okay, so let's think about this question. Why would I not see an I squared anywhere? Well, if the square root of -1 equals I, then what does I squared equal? So think about it for just a minute. I squared would equal Square root of negative 1 times square root of negative 1. What is square root of negative 1 times square root of negative 1? Think about that for a minute while you look at this one. What is square root of 9 times square root of 9? Well, that's 3 times 3, or negative 3 times negative 3, doesn't matter. That equals 9. Square root of 9 times square root of 9 equals 9. What is square root of 4 times square root of 4? 2 times 2 equals 4. What is square root of 100 times square root of 100? You know, you get rid of that radical by squaring a number. That equals 100. So if these are all true, then square root of negative 1 times square root of negative 1 would equal negative 1, right? Okay. So if I is this, and I squared both sides, that would mean I squared would equal negative 1. So I would never leave an I squared in any sort of expression or anything. I would always change that to a negative 1 because I really don't want an imaginary number in my expression or my equation if I don't have to have it there. So if you see an I squared, you need to change that to a negative 1. Let me show you something. Let's say you have 10 plus 3i squared as an answer. Well, if I squared is negative 1, then that would be the same as 10 plus 3 times negative 1, which would be 7, because that's 10 plus negative 3. So anytime you see an I squared anywhere, change it to a negative 1. You got to remember I squared equals negative 1. That you're going to change it every single time. I want you to imagine that you have a parabola. Okay, so x-axis, y-axis. Your parabola is up here. Well, you know that a parabola is a quadratic. And you know that a quadratic has an exponent of 2. And any function that has an exponent of 2 has 2 roots. So you know that this thing has 2 roots if it's a quadratic. But where are they? Does it touch the x-axis? Does it cross the x-axis? No, it doesn't. So if you have a parabola like this, or some polynomial function that doesn't touch the x-axis, doesn't cross it in any way, it still has roots. They are either irrational, such as root 2. Root 2 is an irrational number. Okay, so they're either irrational or they are complex or imaginary, which a complex is a combination of a real and imaginary anyway. So the roots on this thing are either going to turn out to be like a square root of 2 or whatever, or they're going to be complex or imaginary. We can't see them on the x-axis, but we can still figure out what they are. Okay, so I'm going to give you sort of a statement about complex roots. This isn't really a definition, but I want you to write this down because it's something you need to remember. Polynomial functions can have complex roots. In other words, they can have roots that are a combination of real numbers and irrational numbers, or real numbers and imaginary numbers. Complex roots always, underline the word always, appear in pairs. These pairs are called complex conjugates. Underline the word always and underline the word complex conjugates. So what do complex conjugates look like? This is the easy part. If I say this polynomial function has a root at 5 plus 2i. Well, there's a pair. There's a partner for this complex root, and it is 5 minus 2i. So these are complex conjugates. These are the pairs that go together. If I say this polynomial function has a root at square root 2, it also has one at negative root 2. If it has a root at, let's say, 3i, it also has one at negative 3i. Now, if you have a complex number like 5 plus 2i, don't make the 5 negative. You only change the imaginary part to the negative, okay? So that's what complex conjugates are. They are partners or pairs. Anytime you, let me give you an example. If I said you got a cubic function and it has a root at 4 and 3 minus 2i. Well, it's cubic, so it's got to have 3 roots, and none of them bounce or anything like that. Well, you also know that it has one at 3 plus 2i. That is a given. That is automatic. Anytime you see one complex root, you're going to have its conjugate as a root also. So I believe our last objective was to multiply complex numbers. So if you multiply complex numbers, it's typically you're multiplying a complex number and its conjugate. So let me get a pen here. Okay, so if I said multiply 10 plus I times its conjugate, well, that would be 10 plus I times 10 minus I. That's its partner, okay? And you can use box method, you can use FOIL, it really doesn't matter. I'm going to use box method once here and show you what that looks like. So this is 10 plus I. I'm not going to put a plus there, but I will put 10 minus I because we need to remember that that's a negative. 10 times 10 is 100. 10 times I is just 10I. This is negative 10I. And this is going to be negative I squared. So the first thing I see is I see these two things are opposites. They always, always, always cancel out. So when you multiply a complex number times its conjugate, you always have that middle term. It cancels out. So now what I'm left with is 100 minus I squared. Now what did we say I squared is? I squared equals negative 1. So this is 100 minus negative 1. That's 100 plus positive 1. So anytime you multiply a complex number and its conjugate, you are going to get just one number as your answer. You're not going to have an I in your answer. Do you remember I told you that we needed to know how to put things in standard form because when we got to these complex conjugate or the complex roots, we were going to have to multiply this stuff out because we can't put I in Desmos. We can't put it in our graphing calculator. We can't sketch it. We can't draw it. So we have to, we actually have to multiply these together. This is not, obviously these are not roots, but we have to know how to multiply these and we have to know what I squared equals. Okay, let's try another one. I'm not doing box method on this one. I'm going to just do FOIL. 5 times 5 is 25. 2i times, well, we'll do 5 times negative 2i. That's negative 10i. 2i times 5, that's positive 10i. And then 2i times negative 2i, that's minus 4i squared. These two cancel each other out. 25 minus 4i squared equals 25 minus 4 times negative 1. That's negative 1. 25 minus negative 4 is 25 plus 4. That's 29. You got to end up with a real number. So you might have figured this out already. This is kind of like difference of two squares. We don't need to do the middle term. We don't need to do the outside terms or the inside terms. We just need to do the first and the last. 3 times 3 is 9. 4i times negative 4i minus 16i squared. That's the same as 9 plus 16 because this would be minus 16 times negative 1, so that's plus positive 16, so that's 25. Okay, last thing, I want you to pause your video and try this one. See if you can write a cubic polynomial in standard form with roots at 3 and 4i. Okay, if you paused your video and came back, what you need to know is that the 4i is not by itself. Remember, I told you these come in pairs. So if you've got a 4i, you've also got a negative 4i. So the way we would write this is we would write y equals x minus 3, and then we would write x plus 4i and x minus 4i. Remember, it's always x minus whatever, but this right here would be minus negative 4i, and this would be minus the 4i. I can't leave it like this. I have to multiply these things out. I'm going to leave the x minus 3, and I'm going to multiply these two together. Remember, we don't need to do the outside or the inside terms. If we did, it would look like this. We would say x squared minus 4ix plus 4ix minus 16i squared. Okay, these cancel. I'm going to rewrite this part. This is x squared minus 16 times negative 1 is x squared plus 16. And then just multiply these two binomials together. That's going to be x cubed plus 16x minus 3x squared. And what is 16? That's 30, 18, 48. Minus 48. Let's rewrite it in standard form because I'm not quite there yet. X cubed minus 3x squared plus 16x minus 48. So we don't have any imaginary stuff in here if we write it in standard form. All right, that's it. I'll see you tomorrow.